Hello, welcome to Econometrics Melody. In this video, we'll discuss about the chi-square distribution. And before that, let us see some of the useful functions that I use either in calculating the CDF or the PDF of the chi-square distribution. And this is how we can calculate the e to the power Euler number to the power certain values, and e to the power 1. This is what we call is the Euler number, and the e to the power minus 12 is this small number. And another useful function, the natural logarithm of certain numbers, and the base for the natural logarithm is the Euler number itself. So we cannot calculate the natural logarithm of 0, it is undefined, and the natural logarithm of 2 points, the Euler number, it is 1, and the natural logarithm, exponential and natural logarithm, they are inverse to each other. That is why we get the same input is the result. Now let us see the example of the relationship between factorial and gamma. We know that gamma n is equals to n minus 1 factorial, and which is evident by this example as well. So the factorial of 8 is equals to gamma 9, and the gamma 12 is equals to factorial 11. We cannot calculate the factorial of decimal values, while we can calculate the gamma of the decimal values. Now let us see some of the formula of the chi-square distribution, and we will calculate the PDF, CDF in our next session. First of all, the value of mean is equals to degrees of freedom, and its variance is equals to twice the degrees of freedom. PDF of the chi-square distribution, it is calculated by x to the power half the degrees of freedom minus 1 and Euler number to the power half the value of x whole divided by 2 to the power half the degrees of freedom and the gamma value of half the degrees of freedom. Similarly, the CDF is calculated by taking help of this lower incomplete gamma function for this parameter, half the degrees of freedom and half the value of x, whole divided by gamma half the degrees of freedom. Now let us say the gamma function, we integrate it from 0 to infinity, and we raise 2 to the power this variable z minus 1 and e to the power minus t dt, and gamma z is equals to 0 minus 1 factorial. We have seen in our example in our earlier session, gamma n is equals to n minus 1 factorial, and which further is equals to z minus 1 into gamma value of z minus 1. So when we integrate from 0 to infinity, this is a complete gamma function. Now for any value of x lying between 0 to infinity, if we integrate it from 0 to x, then it is the lower incomplete gamma function, and if we integrate it from x to the upper bound infinity, and it is called as the upper incomplete gamma function. Now we will calculate the CDF of chi-square distribution for these three examples, and we will use the quadrature class in Mata, and I will use Stata version 17 to calculate that. It is supported from Stata 16 onwards. What is the probability of x being less than or equal to 6 for a chi-square distribution with the degrees of freedom equals to 9? First of all, let us calculate its lower incomplete gamma function. So half the value of x is 6 divided by 2, 3. So we integrate from 0 to 3. And our lower incomplete gamma function, this is the one, x to the power half the degrees of freedom minus 1 and e to the power x. Let us see what do we get. What is the value of the lower incomplete gamma function? It is 3.02, and which we have substituted it over here, 3.02. This is the generic way of calculating the CDF of the chi-square distribution. Lower incomplete gamma function divided by gamma of half the degrees of freedom, 0.26. Chi-square, it is the Stata function to calculate the CDF of a chi-square distribution for the given degrees of freedom and an x. Now let's see, both of them should yield the same result. It is 26%. Now this is the Econometrics Melody written program to calculate the CDF of a chi-square distribution for given degrees of freedom. And let us see, if the value of x is 6 or less, the probability is 26. 6 or less, the probability is somewhat 26, somewhere over here. Now let us see another example. So the degrees of freedom is 15 and the value of x is 12. So degrees of freedom is 15, that is half the degrees of freedom is 7.5, and we integrate from 0 to half the value of x. So x is 12, so half of it is 6. Now let us see what is its lower incomplete gamma function. First of all, let us calculate it, and it is 600.61, and we, in our generic formula, we use this value, lower incomplete gamma function divided by the gamma of half the degrees of freedom, and both the formula, it should yield the same result. So the probability of x being less than or equal to 12 for the degrees of freedom 15, it is 32%. Less than equal to 12, it is 32%. Less than equal to 12, it is 32%, somewhere over here. Now let us see another example. This time we are going to take the degrees of freedom to be 30 and the value of x is 28. So the half the value of 30 degrees of freedom is 15, and we integrate from half the value of x 0 to half the value of x is 28. And let us see what is our lower incomplete gamma function. Its value, it is 3 point this value over here, and in our generic form we divide this by the value of gamma, half the degrees of freedom. Both of them should yield the same result. It is 43%. So when the degrees of freedom is 30 and the probability of getting 28 or less, it is 43%. 28 or less, 28 or less, it is 43% somewhere over here, and this is it. Now let us calculate the PDF of the chi-square distribution, and the chi-square then it is the Stata function to calculate the PDF of the chi-square distribution for this degrees of freedom and the value of x. And this is our generic formula where we use x to the power half the degrees of freedom minus 1 and e to the power half the value of x, 2 to the power half the degrees of freedom, and gamma half the degrees of freedom. So let us see, both of them should yield the same result. It is 10%. So when the degrees of freedom is 9, the value of getting exactly the value of x to be 6, the probability is 10%. So when the value of x is 6, 5, 6 somewhere over here, and it is 10%. At the backdrop we have a normal distribution with the mean and variance equal to the mean and variance of this chi-square distribution. Now let us see another example. This time the degrees of freedom is 15 and the value of x is 12. So what is the probability of x being exactly 12 for the chi-square distribution? So it is 7.5%. So at the value of x 12, it is 7.5%. This percent somewhere over here. Now let us see another example. When the degrees of freedom is 30 and the value of x is 28. So from both the formulae we should get the same result. What is the probability of getting x 28, exactly 28? It is 5.2% or 5.3%, and let us see it by the half of graph as well. For 28 it is 5.3% somewhere over here. Now let us compare the graph of the chi-square distribution, one by the generic formula and one by the Stata function. This one on the left hand side we do it by using the formula, it's a generic formula, and the second one on the right we do this graph by using the chi-den function of Stata. Now let us draw the chi-square distribution for different degrees of freedom ranging from 1 to 10 in this case, and this is the program that we have written for degrees of freedom 1, 2 all the way to degrees of freedom 10, and we see how the nature of the chi-square distribution it changes. Now let us draw the chi-square distribution for some degrees of freedom in a single graph. We are going to draw the chi-square distribution from 1 to 6. So let us repeat the same process, but this time the degrees of freedom increases from 3 to 12. Now let us repeat the process, but this time we are going to increase the degrees of freedom from 12 to 21. So as the degrees of freedom increases, slowly we'll get a bell-shaped curve. And let us repeat the process, but this time with a very high degrees of freedom from 297 to 306. So we want to see that for the larger degrees of freedom, the chi-square also converges to the normal distribution. And at the backdrop we have a normal distribution, and at the forefront with this red line we have a chi-square distribution, and we see that nearly both of them are converging. The chi-square distribution is converging to the normal distribution. And let us this time increase the degrees of freedom to 600, and let us see whether the normal distribution and the chi-square distribution they are same. Yes, they are one and the same. Now let us see another program, the area graph of the chi-square distribution. This is useful for the hypothesis testing, and chi-square distribution is generally a right tilt test. So we see the p-value for the value of x being greater than 12. Our calculated chi-square is 12, so greater than it is 44.57%. So in this case we fail to reject the null, and towards the right we have a 5% significance level or alpha value of 5% marked by this yellow color. And along with this area graph, if we want to draw the normal distribution, we have this another program, chi-square area, and n stands for normal for the given parameter degrees of freedom and chi-square value. So at the backdrop we have a normal distribution. It is the same graph, the only difference is that at the backdrop we have a normal distribution with the mean and variance equal to the mean and variance of this chi-square distribution. Similarly, another program chi-square two-tail TT area, this will depict the two-tail information for the two-tail test, and which is very rare in chi-square distribution. Let us say, so this is the left. On the area portion marked by the yellow, it represents 2.5% of the area, and on the right marked by yellow, it represents the 2.5% of the area, and when we add it up, it is equal to the alpha value, that is 5%. So this red dotted line, it represents the calculated chi-square 12. So towards the right of it, it covers 44.57% of the area, and towards the left of it, it covers 55.43% of the area. So in either of the cases, so we fail to reject the null in this case. So we have already discussed about the tabulate of table of frequencies in video number 10, miscellaneous series of Stata. In that video, we have also covered about the chi-square test. Now let us see the data from the same video and then perform the chi-square test. This time we are going to show the graphical depiction. Now let us tabulate the body and pay. These are the categorical variable, and we want to display the expected frequency as well as the row percentage and column percentage, and also display the chi-square value. So the first row, it represents the natural frequency. So there are 84 people who are fat and who prefer to pay via cash out of 300 people. And the second row, it represents the expected frequency, and the third row, it represents the row total, and the fourth row, it represents the column total. Here the variable body and pay, they are the categorical variable, and we want to test the hypothesis that whether the categories are independent or there is some sort of association or some sort of dependence. And we have 1 degree of freedom, and its p-value is 0.04. And this program is going to depict the same information in the graph, and let us say it, and we will make the hypothesis. So our calculated score, it was 8.42, and for the right tail, the p-value was 0.37%, meaning thereby the area towards the right of this line, it is 0.37%, and toward the left of this line, it is 99.63%. So we don't belong to this region. It is very clear by this graph. So we reject the null, which implies that there is some sort of association between these variables body and pay, and we are going to further identify the point of association. And let us say this is again the same tabulation and the same graphical depiction. It is a kind of a repetition. So we reject the null hypothesis of no association, and we conclude that there is some sort of association. Let us identify the point of association. So the same information from the table has been written over here. So in the first case, whether the fat people or the thin people, they prefer cash. So here the percentage for the fat people is 60%, and the percentage for the thin people is 40%. So we are going to use the proportion test, and which will display the Z score, and we will use our area program to display this information. The Z score is 2.32, and we have 98%. Let us remember this single tail and two-tailed p-value, 98, 2 and 1. 98, 2 and 1, and let us say 98, 2 and 1. So for the two-tail test, it is very evident that this threshold of 1.96, we were not able to exceed or surpass this. That is why we reject the null for the two-tail test, either based on the p-value or based on the score, Z score. Now let us see our one-tail test. So in one-tail test, we reject the null for the right-tail test, and this represents that x is greater than y, which in our case represents that fat people use more cash than the thin people. While for the left tail test, we fail to reject the null in this case. So we conclude that the fat people use more cash than the thin, which is also evident over here. Here we reject the null in this case when the difference is greater than 0. When the difference is greater than 0 only when x is greater than y, which means x is fat and y is thin. So fat people, they prefer cash in comparison to the thin people. Now we will draw similar inferences, and if we see the percentage, fat people have 75%, and thin people, it is only 25%. So in terms of kind, so whether fat people prefer more kind payment or the thin people, and we see that the fat people prefer more kind payment. So in the right tail test, we reject the null. So x is greater than y. In this case, we are saying that x is greater than y, which means that fat people use more kind payment than the thin people. And in case of left tail test, we fail to reject the null. In case of two tail test, we reject the null. So there is some sort of association. We see that fat people use more kind payment than the thin people, because X is a right tail test, we reject the null. Now let us repeat the process here. Fat people, sorry, cash payment for the fat people, the cash payment is only 40% and the kind payment is 60%. Let's see whether it is true according to the hypothesis or not. First, let us run the proportion test, and let us remember this score: minus 2.5 and 0, 1 and 99. Minus 2.5, 0, 1 and 99. Minus 2.5, and this is nearly 0, 1 and 99. So for the two tail test, we reject the null, and for the left tail test, again we reject the null, and we conclude that kind payment is popular among the fat people. So this is some sort of association we have established. So kind payment is more preferred to cash by fat people. Now let us keep the thin people constant. Let us see which mode of payment is popular among the thin people, cash or kind, and which percentage more. Cash percentage is more in this case. So cash payment should be more popular among the thin people. Let us see whether this statement is supported by the test as well, proportion test. The JD score is 1.71, and in this case we fail to reject the null. In this case we fail to reject the null, and in this case we reject the null. And let us depict the same information by our area graph and make certain analysis. And we see for the two tail test we fail to reject the null, either based on the p-value or based on the JD score. And for the left tail test, the p-value is greater than our alpha level, that is why we fail to reject the null. And for the right tail test, at the 5% level, then we reject the null. But this is nearly equal to 5%, but still we can say that among the thin people, cash payment is more popular. So these four tests, it established some sort of association among the categories of these two variables, body and pay. And we have rejected the null hypothesis of no association. This is what we wanted to prove. Now let us see another example, and this is we can also perform the Fisher-Exact test, and Fisher-Exact test is useful to determine if non-random association between two categories, whether it exists or not. And let us say the p-value is 14%, so we fail to reject the null, and we conclude that there is no association between these two variables. And graphically it is very clear. Our significance level is 5% and our p-value is 13.36%. So we fail to reject the null in this case, and we conclude that there is no association between these variables. And we get the similar result when we perform this likelihood ratio chi-square value. First of all, let us see its tabulation, and for the degrees of freedom 2, the chi-square value is 4.02 and its probability is 13.3. So we fail to reject the null, and let us further prove it by our graph. If the p-value is greater than our alpha value, that is why we fail to reject the null, and we conclude that there is no association. Now let us see 4 more examples of hypothesis testing in chi-square. So chi-square area, this is the user written program, and we can provide the value for degrees of freedom and the chi-score as well as the significance level. And let us see what does the graph look like. The degrees of freedom is 12 and our calculated chi-square is 10 over here, and we want to test the right tail test, and the significance level is 5%. And by the very graph it is clear that the probability of x being greater than 10, it is 61.6%. So this is our p-value. P-value is greater than our alpha level, that is why we fail to reject the null. So the probability of chi-score being less than 10, it is 38.4%, this region. And this is also again greater than 5% alpha value, that is why we fail to reject the null in this case as well. But generally in chi-square we perform the right tail test. Now let us see another example. If a distribution follows a chi-square process, so having a degrees of freedom 3, and what is the probability of the chi-square score being greater than 9? So our calculated chi-score is 9, represented by this dotted line, and our significance level is 5%. For this 5%, what is the score? It is 7.81, somewhere over here. And from the graphical depiction, it is very clear that we are away from this threshold, that is why we reject the null in this case. In another word, is the p-value is less than our alpha value, that is why we reject the null in this case. Now let's see another example. If a certain process follows a chi-square distribution with the degrees of freedom to be 6, and we want to test a hypothesis whether the chi-square is score is greater than 11 for the significance level 5%. So graphically, it is very clear we are able to surpass this threshold of 5% significance level. So in this case, we fail to reject the null. As the p-value is greater than our significance level, that is why we fail to reject the null for the right tail test. So last but not the least, if a certain process follows a chi-square distribution with the degrees of freedom 20 and at 1% significance level, can we test that the chi-square score is greater than 40? So seeing the significance level, this time we have taken it to be 1%, and our calculated score, so its p-value, it has generated 0.5%, and we think the graph we can outright reject the null hypothesis because the p-value is quite less than our significance level. Now let us see some important notes and properties of the chi-square distribution. We can calculate the value of chi-square by summing observed minus expected and its square divided by expected I for the ith observation. So degrees of freedom, k degrees of freedom in a chi-square means that we have summed the square of k independent standard normal, meaning thereby the normal distribution with mean 0 and variance 1. We have summed the square of k independent standard normal random variables. Now let us say some of the uses of the chi-square distribution. Goodness of fit test. This test is used to determine if a sample data set fits a specific distribution. Chi-square is used for the test of independence. This test is used to determine if two categorical variables are independent of each other. Chi-square is also used to perform a test of homogeneity. This test is used to determine if two or more categorical variables have the same distribution, and it is also used to perform ANOVA analysis. The chi-square distribution is used in one way and a two-way ANOVA to determine if there are significant differences between group means, and it is also used in determination of confidence interval for a population proportion. Can be used to construct a confidence interval for the population proportion. Non-parametric test, chi-square test and its variant are used in a non-parametric test to compare data in contingency table. In time series analysis, the chi-square distribution is used to test for the independence of data in time series analysis. For power analysis, the chi-square distribution can be used in power analysis to determine the sample size needed for a study in order to achieve a desired level of power. In survival analysis, the chi-square distribution is used in survival analysis to test for differences in survival rates between groups. In quality control, the chi-square distribution is used in quality control to determine if a process is producing items that meet a set of specifications. In regression analysis, the chi-square distribution can be used in regression analysis to test for the independence of residuals. The chi-square distribution can be used in feature selection for machine learning algorithms such as decision trees and naive Bayes. Chi-square is particularly useful for analyzing categorical data and testing for independence and homogeneity among variables, and it is used in many other fields. So this is it for this tutorial. Thank you very much for your time. Thank you very much, Econometrics Melody.